All right, in this video, I'll be going over the differences between gram-positive and gram-negative bacteria. The first difference is going to be the cell wall composition. For the gram-negative bacteria, there's going to have multiple layers. We're going to have the periplasmic space, the cytoplasmic membrane, and then the most important part, the LPS layer. And the gram-positive will have the cytoplasmic membrane, the peptidoglycan wall, and the periplasmic space. Now, if you learn these differences in the cell wall composition, everything else should fall into place. So make sure that you do memorize what components each one has. So both have this cytoplasmic membrane, which is the bilipid layer with the polar heads and the fatty acid tails. All right, next we have the periplasmic space. Here, where they pump out protons for the electron transport chain. Now, the difference in gram-positive here and gram-negative is that gram-negative has more space in the periplasmic space, so they're able to store substances in this area as well, other than the protons. And gram-positive probably can, but not as much as gram-negative. Next, this is a big difference. Gram-positive has a 90% cell wall composition peptidoglycan wall, while the gram-negative has only a 10% composition of the cell wall. Next, you would have the different structures within the cell wall. So for gram-negative, you'll have these teichoic acids, which go through the peptidoglycan wall onto the other side of the cytoplasmic membrane. And then you have the lipoteichoic, which are rooted in the cytoplasmic membrane that basically anchors this wall into this membrane. Then we have wall-associated proteins used for cellular functions. So this is teichoic. And this is lipoteichoic. Oh, I might have not spelled that right. Okay, so after that, the gram-positive is going to be a little bit more complex. On this one, you would have the peptidoglycan wall, then you would have another periplasmic space, and then you would have another bilipid layer. And in the second bilipid layer, you'll have the LPS anchored into it. All right, and then we have a couple porons. Porons that go through, they let substances in and out. All right, and then we have the LPS. LPS has a lipid A component that anchors the LPS into this bilipid layer, but it's also used as an endotoxin. So that's when this part of when a bacteria is lysed during, like, say, if they're using antibiotics or antibodies lyse them or something like that. Usually it's antibiotics that will do it at an alarming rate. It would cause a severe shock response in the host cell. So that's why doctors tend not to, if they want to be careful, they don't shove antibiotics down someone's throat, or they don't give a lot of antibiotics at the same time, because it may the bacteria that they're infected with might release this lipid A and cause a severe shock response. So this is an important defense mechanism in the gram-negative bacteria. The next part of the LPS is going to be the core polysaccharide. Now, these are common polysaccharides. They don't change in structure like this next component does. Now, this next component is going to be the O antigen, and the O antigen actually works as a cloaking device for the gram-negative. So when you have an antibody looking for a specific bacteria, if you look at the cell, you'll see the O antigen. Now, if your antibody is looking for a purple, say a purple O antigen, even though it's not, I don't know if it's denoted by color, but if you're looking for a bacteria that looks purple, this O antigen can change configuration and to say it'll look orange. So the antibody is not able to recognize this usually pathogenic or this pathogenic bacteria like it would usually. So that is another great defense mechanism for the gram-negative bacteria. And that's what makes it highly pathogenic versus the gram-positive, which tends to be non-pathogenic. So we have the peptidoglycan wall, and then these different structures between the two. The next difference comes back to the cell composition. It's the reason why that the flagella morphology is different. So we have the gram-positive up here, gram-negative. Because gram-positive have such a thick peptidoglycan wall, they don't have to have multiple rings around their flagella structure versus, say, something else that doesn't have that much of a layer. That layer acts as a way to stabilize the flagella, so when it spins, it doesn't have a lot of torque, and so, or it doesn't, yeah, it does have a lot of torque, it increases torque, so it makes it more stable when it spins during movement. So we have the hook here, the filament that comes out of it, and then the rings, the two base rings. And this is based into the base body. So that's basically just the bacteria down here. So we have the hook, we have the spinning motion, we have the base body where it's rooted in, then we have these two rings. It only has two rings in the base body. Now, gram-negative is going to be different. So you know that in a gram-negative, they only have like a 10% composition of peptidoglycan in the cell wall. So it doesn't have a lot of structural integrity. So what it needs is two more rings that is rooted in the outer membrane and then some in the base body. So you'll have the base body, these two rings, so we have a total of 4 rings. All right, and the filament and the hook. So that stabilizes it whenever it's being spun around during motion. Right, and the next difference is the gram stain. Now, in the gram stain, again, it goes back to cell wall composition. Gram-negative and gram-positive have different levels of lipids in the cell wall. So for gram-negative, they have a good amount of lipids in their cell wall versus a gram-positive, which is 90% peptidoglycan. It does not. So when you go through the steps of the gram stain, because of this thick peptidoglycan layer, it's periodic space, and then when it's covered in dye, it holds steadfast longer than it would in a gram-negative. Now, the steps of the gram stain goes by this. It goes, you have 1 minute of crystal violet, then you use, and this will give purple dye. Then you have the iodine, which basically lets the violet soak in harder, so it's harder to remove. And then you have the decolorizer, which is, we use acetone alcohol. And then the safranin. So And a gram-positive in the first step, both actually are dyed purple. Even though they're different, just bear with me, I'll go through every step. So we have the cytoplasmic membrane here. And then periplasmic space, peptidoglycan wall. Then we have another bilipid layer. And then we have the LPS. So when it's dyed, it actually goes through both pretty well. So then both is purple here. And then next, the iodine basically just sets it in. You let it sit for 1 minute with iodine, then it sets the purple in deeper. So it's harder to remove when we do the decolorizer. But the decolorizer is made of acetone and alcohol, which both dissolve lipids really well. So because gram-positive doesn't have that many lipids, it doesn't dissolve the dye out as easy as it does with gram-negative, which has 2 bilipid layers and then has LPS and all that. So the lipids with the dye here are washed out, and it takes the dye with it. Now, after that happens, we use safranin, and safranin will just come back and dye the gram-negative pink while the gram-positive is still purple. So that is where the difference comes under the gram stain. It's all because of this cell wall composition. That's why it's so important that you learn the differences between the two before you go any further in micro. But basically, those are the 3 differences that you can list, say, on a test. If they ask you, how would you be able to distinguish the 2? These are the different steps. And I actually have a picture of a gram stain under a microscope, if I can get it to focus. Okay, so this is a gram-negative and gram-positive under a microscope. And the purple is going to be the gram-positive, which is that thick peptidoglycan wall. It holds in that purple dye. And then you have the pink, which is the gram-negative, which is dyed pink when the safranin is used in the final step. So those are all actually the differences that I have concluded are great in distinguishing between these 2 bacteria.